Hello everyone, welcome to the YouTube channel of Yourpedia and Engineering Career Points. I am Vinish Sharma, your mentor of mechanical engineering here. So as you know, the BEL has announced the vacancies here and the module has been started by the Yourpedia and all the live classes are going on. Okay now. And in this particular video, I am here to give you some basic information related to the paper analysis here. Along with that, we are going to see some the part of the finite element method also. Okay now. So this was the simple paper analysis which I have already done here. Okay, and you already know that which subject is important for you. And here we have seen that in 2025 exam they have included the two different subjects here. The first one is the finite element method. Okay, the finite element method here, and the second one is the engineering drawing. And out of these two subjects, 8 questions has already been asked, 4 from each particular subject here. So I can say that almost 4 to 5% has been weightage has been given to this particular subjects here. Okay na? So even though if you just see the finite element method, if you talk about this subject is a very it is a little bit tricky, difficult subject here. Okay, and it is not generally covered in the graduation part. Okay, this is basically studied in the post graduation part. But the question which has been asked from the finite element method, they are very simple, because if you can see the objective questions cannot be framed from this particular subject here. Okay, so generally they ask you the question related to the one-dimensional problems here. They ask you the question related to the elements here. Okay, which type of elements we use. Okay, and how do we what is the use of FEM, why do we prefer the FEM here to analyze all the structural problems here. Okay, this type of questions are normally asked from this particular subject here. So we are going to see one by one that what is the meaning of FEM, what is the need here of studying this particular subject. Along with that, how many type of different elements we have seen in the particular these subjects here. Okay, now how do we do the analysis also. So if we talk about the finite element method here finite element method here, you will find first of all what is the meaning of finite element method and what is the requirement here. If you just see, the main purpose of studying the engineering is to solve the physical problems. Okay, now and if you want to solve the physical problem, what we have to do, we have to convert the physical problem into the mathematical form here. Okay, so what do? We do some mathematical formulations here of any physical problem, then we find out the solutions of the mathematical equations here, and after finding the solutions we can relate it to the physical problems also. So in the classical analytical method which we used earlier before the FEM here, they basically considered a differential element. If you just see, whenever you are studying any particular subject like any particular subject of engineering here, you always define a differential element here, and then you just start the your analysis part. Okay, we define the boundary conditions, we define the particular differential equation over the differential element, and then we integrate it. So that is the procedure to solve the problem. But if you just see, if we talk about the real life problem, okay, because in the thread in the books here you have also understand, you can see here that whenever we are solving any particular problem, we always take some assumptions. Okay, like in the case of Bernoulli's equation. Okay, we have taken the assumption as fluid as incompressible, fluid is inviscid. Okay, now the fluid is flowing along a streamlines here, but in practical scenario that is not a case here. Okay, the assumptions are not validated there. So at that point in the real life problems, if you just see, they are very difficult, complicated problems here. Okay now, so I can say in the case of real life problems, it is very difficult to obtain an exact solutions of the governing differential equations here, which are in the form of partial differential equation. Why? Because we have a complex geometry. Along with that, we can say we may have a number of boundary conditions also. Okay, now what how this problem can be solved. So here we use a finite element method. Okay, a procedure to solve this type of problems here. In this case, what we do, we actually convert the, I can say we actually transform the governing differential equation into the some another form here. Okay, or we just try to find out the approximate solutions here. Okay, so you can see FEM can be viewed as a method for finding out the approximate solution. So now you can see this is the approximate solution, so there may be a chance that we have an error into our calculations here. Okay now, or we make transform the partial differential equation into the different forms. Generally here, whenever we define the differential equation, they are normally defined in the weak forms. Okay, because the weak form analysis is very simple as compared to the actual governing differential equation. So just remember that part. Okay, so how do we start it? First of all, as I have told you that in the actual problems, in the classical analytical methods here, we are defining the differential element, we are defining the governing differential equation. Now in this case, what we do, we start with the trial solutions here. We have to start with the trial solutions. Okay, and we have to make ensure that this trial solution which we are assuming, they should satisfy the boundary conditions. they should satisfy the boundary conditions here. Along with that, it should solve the differential equations here. Okay, now the boundary conditions should be solved here. Next part here. So here in this case, if you just see, the trial solution is does not going to solve the exact differential equations here. There may be some error induced in this. So I can say whenever you are using the trial solution, they always leave the domain residual. Domain residual simply means the error. Okay, it is basically the error which is basically induced while defining the trial solution. Now in this case, what we do, we are discretizing the body into a different type of elements here. Okay, we have a number of node points, and each and every node point we are doing our calculations. So you can see the domain residual at each and every node is going to be there. Okay, so I can say in the entire domain here, what will happen, the domain residual will be keep on adding here. Okay, so that is why we calculate the weighted sum of the domain residual in the entire domain here, and we have to make ensure that the weighted sum of domain residual computed should be 0 here. But it is not a practical scenario here, because it cannot be made 0 exactly. So we try to minimize it as much as possible here. Okay, now in this case, as I have told you that we start with the trial solution, then what we do, the accuracy of these trial solutions are basically improved by including the higher order terms here. Okay, now by including the higher order term, what we try to do, we try to improve the accuracy of the solution. So let us say if you are using the first order terms here, okay, or linear order terms here, we may have a higher amount of error induced. So if you are going for a quadratic, or if you are going for a cubic polynomial here while doing the calculations here, then you may say that we are trying to reduce the error here, and we are improving the accuracy of the results. Okay, but the problem is that whenever you are shifting to the higher order, in that case the computation time keep on increasing. The computation become very difficult here. It requires a large amount of resources, which is not practically feasible here then. Okay, so now, and another problem is that defining a continuous trial function is a very difficult task, because we have to make ensure that this trial function, okay, it should be continuous and it should be valid over the entire domain here. Okay, so there may be a chance it is not entirely valid here. Okay, now what we are doing in this FEM here. So this is a simple procedure by how we are proceeding in this particular subject here. Now in this case, what we do, the domain which we have is discretized into the different type of elements here. It is discretizing into the several elements here, and we may have a different shapes of element also, depending upon whether we have a 1D structural problem here, whether we have a 2D problem here, or whether we have a 3D problems here. For example, if I just show you the different type of elements here, you can see, okay, these are the shape of the common 2D elements here. Okay, and similarly, if you just go through here, in this case you can see we may have elements in this shape for the plate and shell, as well as for the 3D structure we may have an element as like this one here. Okay, so different type of elements we may define. Now in this case, if you just see, each element is made up of elements here which is known as the node. Now in this case, generally a node is having a 6 degree of freedom. A node is having a 6 degree of freedom, that is 3 translation motion is going to be there at each node, and 3 rotational motions are going to be there at each nodes here. Okay, now so in this case, if you just see, if I just talk about the general frame element here, in this case one node we are having a 6 degree of freedom. You can see here 3 translations, along with that 3 rotations here about its point. Okay, so just remember that they may ask you the question here that what type of elements are there in the FEM method here. Second thing, how many degree of freedoms are going to be there. Okay, and in the case of 1D element, 2D element, or the 3D element here, how we segregate the degree of freedom, how we define the degree of freedom there. Okay, this type of general questions are normally asked. Now coming back to the questions here. So first here you can see, what question can be asked here. So which of the following is an example of 1D structural finite element here. So now just see, we are talking about the 1D structural finite element here. Okay, and what are the options? Plate element, bar truss element, shell element, solid element here. So whenever we are talking about the 1D structural element, in that case you can see the plate element is basically of the 2D is our 2D element here. Okay, similarly shell element, solid brick element, they are the further type of the 2D and 3D elements here. Okay, na? Only the bar and truss element is representing a 1D structural finite element here, because it have a displacement only along the one direction here. So let us suppose if you have a single bar here, so I can define two nodes here, one at each point. Okay, and each node is having only 1 degree of freedom, because in this case you can see this rod can translate only in axial direction here. So I can say that the node which has been defined at each end, they may have a displacement at each in the axial direction only. Okay, so remember that in the case of 1D structural finite element, it represents that those structures where the deformation occur only along one dimensions here. Okay, it may have a axial displacement, it may have a longitudinal displacement here. Now the bar or truss elements, I have already told you, that are the examples of the 1D structural finite elements here. Okay, and they are basically used to model the structures also. Second, plate element and shell element, I have shown you, they are basically the 2D elements here. Okay, so they generally represent those structure in which we may have a bending or we may have a torsion effect here. Okay, in the 2 dimensions. Second, in the case of solid element, if you just see, we have a 3D configuration. Okay, so they are generally used for the volumetric dimensional changes here. Okay, now in the FEM. So just remember this one, this is a little bit important part for you. Now coming back to the next question, a bar under axial loading is represented by the 1D finite element model. Okay, what is the number of node in the model if the bar length is split into 3 equal elements here? So if you have just see in this case, we have a simple bar. Now this bar has been represented by a 1D finite element model here, and we have split it into the 3 equal elements. So let us suppose 1, 2, 3 and 4. So here I can say I have 3 elements. The first one is this one, second one is this one, and third one is this one. So if I want to define the nodes, so I can say here the one node is at point number A, the another node is at point number B, and other node is at C and D here. So total number of node in this case, how many nodes are going to be there? There are 4 nodes. Okay, so if I talk about the one structure, let us suppose if one element is there, like this one, in this case what will happen? You are going to observe that we are having the 2 nodes, one at the each end. Okay, so one element is having a 2 nodes, one at each end here. Similarly, if you are defining the 1D structural element with the help of 3 elements here, the corresponding number of nodes will become equal to number of elements plus 1 here. Okay, so just remember that whenever you are defining the number of nodes, the number of nodes formula will become equal to number of node formula. I am talking about the 1D structural elements only here. Okay, because you don't have to go into detail, don't worry. Okay, so just you can see the number of nodes, the number of node is going to be equal to number of element plus 1. So let us suppose if you are representing it by the with the 5 elements, in that case how many nodes are going to be there? 6 nodes are going to be there. And also remember, in the case of one dimensional structure element, each node is having a 1 degree of freedom only. Why 1 degree of freedom only? Because this element can translate, or this element can I can say this element may have a deformation only along the axial direction here. Okay, now it may have a displacement only along the axial direction. That is why this is having a 1 degree of freedom. If the element is of 3D configuration, let us say 3D structure here, in that case I can say that element may have a 6 degree of freedom here. Okay, so in this question what can be the answer here? The 4 can be the correct answer. The total number of nodes will be 4. Next part, for a 1D linear bar elements, how many nodes does a single element have? We have seen that. Okay, in that element in this case we have seen, in the case of 1D structural element, how many nodes are there? Only 2 nodes are going to be there. Okay, so that's a simple case. Okay, anything else here? Yeah. Now coming back to the next part here, which of the following is an example of 1D structural? Oh, just give me a second. That is the same thing, no? Yeah, just give me a Yeah, so here we have seen this question here. Yeah, this one here. Now if a bar of length is divided into n equal elements, then what will be the number of node in the system? So in this case again you can see the number of element are n. The corresponding number of nodes will be n plus 1 here. Okay, that's again a simple case. Now the next thing is for in the finite element method, the degree of freedom per node for a 1D axial bar element in an axial loadings are, that is again 1 here. Why 1? Because the node are going to experience the deformation or the displacement along the one direction here only. Okay, that is why we are having only 1 degree of freedom. 5 degree of freedom has 5 different motions has been constrained here. Okay, now so in this case only 1 degree of freedom will be there. Now just see one more thing. Here we have seen that what is the requirement of FEM. Why we prefer the FEM over the classical analytical method? Because in the classical analytical method we have a partial differential equations which are not easy to solve. But in the case of FEM, what we are doing, we are representing any particular 3D body or a 2D body into a discretized element here. Each element is consisting of some nodes. Each node is having some degree of freedom here. Okay, now what we do, we just try to write down the relation. We just try to write down the differential equation for each particular elements here. For example, if you just see why the FEM becomes so much famous here. Why FEM becomes so much famous? So let us suppose if you have a differential equation like this one. If you have a differential equation like this one, this simple equation, this simple differential equation is generally used to solve the many problems here, many engineering problems here. You can solve the problems of axial deformation here with this governing differential equation. You can solve the problem of heat transfer with this governing differential equation. So let us suppose if you want to solve the problem of a SOM, okay, axial loading case. In that case, what does the Q will represent? Q will represent the force which is acting, axial force here. Okay, just remember that it is representing the axial force. Similarly, if you want here you can see again A is representing the area of the cross section here. It may represent the area of cross section. And the next thing is C. C will represent the Young modulus here. Young modulus of the bar here. Okay, if you just try to solve the structural problems here. Okay, now and F is representing the axial deformation here. Axial deformation here. Now let us suppose if we talk about the heat transfer problem here. Okay, generalized heat conduction problem here. In that case, what will happen? If you just see, in that case, the A will represent again the area of cross section here, area of the cross section of the element or a body here. Okay, C will represent the thermal conductivity of a problem, here. Next, what will F represent here? F will represent the temperature here. Okay, now it is representing the temperature, and correspondingly the Q is representing the heat transfer, rate of heat transfer here. You can say rate of heat generation inside the body here per unit volume. Rate of heat generation per unit volume which is taking place inside the body. Okay, so you can see just with the help of a simple differential equation, what we can do, we can solve the different type of engineering problems here. So there comes we see the usefulness of the FEM. Okay, so depending upon the type of problem, we may have a different type of we may perform the different type of analysis here, and the FEM can simply be integrated in all the particular subjects here. Okay, so that's a very simple case. Now next part is what we have to study in the FEM. First of all, just see FEM subject is little bit tricky. Okay, they cannot ask you the very much detailed questions from this particular subject. They may ask you some basic theoretical questions related to the I have already told you that nodes, elements, second analysis of the one dimensional structure here, or they may ask you the how to formulate the stiffness matrix here, because in the case of final element method, whenever you are doing the analysis of a node or an element, we define a particular stiffness matrix here. You are going to see it later on. Okay, now what will be the dimension of that stiffness matrix while solving the problem. We may find all of those things in the FEM layer. Okay, now so question related to this much part is only required for you. Okay, so just make ensure that you will cover up the basics of the FEM. That will be sufficient here. Okay, anything so you can see I have already covered the first half of the FEM part here. Okay, so just extend this analysis to the two-dimensional also. Along with that, just see the formulation of the stiffness matrix here. Okay, that will be sufficient for the particular subject here. Okay, now so that's it for this particular video here.